2020 was a year that challenged all of us, across the globe, in fundamental ways. From the global pandemic to the raging wildfires exacerbated by climate change, one critical thing became clear. Changes must be made now to ensure a safe and healthy future in which humans can live and perform at full capacity. The renovation of 1021 presented an opportunity to put this intention into action. How could we reevaluate the performance of 1021 such that the building could become a living model of a resilient future, one that could adapt to a pandemic, withstand natural disasters, and combat climate change? We took the Zero Energy Building Challenge one step further. Not only did we design for optimizing performance of the building systems, but we also focused on optimizing the performance of building occupants.
The nature of the 1021 building's purpose in the Virginia Tech School of Architecture and its position in the heart of Alexandria's Old Town present additional challenges beyond the scope of a typical sustainable retrofit. Local codes require strict adherence to design guidelines which reflect the values of the historical neighborhood, and the residential zones bordering the site restrict the height of the building. The operational needs of an expanding architecture program in the National Capital Region put forth a unique and demanding program that combines traditional office spaces with specialized workshops and gathering areas. These constraints help to shape the overall goals of this project. The basis of this overhaul is to bring the current building envelope up to thermal performance standards by adding layers to the existing envelope. This method of addition, and not replacement, drastically reduces construction waste. New exterior assemblies increase construction efficiency and reduce thermal bridging. The envelope is completed by a new facade, which maintains the sensitive materiality of Old Town Alexandria by using materials that interpret traditional building methods in a contemporary way. The project applies reused and sustainably sourced facade materials designed to have a long life cycle and to be fully recyclable. The building's footprint is enlarged with masses carefully applied inward to the site, which prevents the 1021 building from overwhelming its human-scaled neighborhood. Modern architectural elements, like passive shading devices on the east and west facades, reinterpret traditional architectural elements in a modern and sustainable context. Within the 1021 building, natural and passive building systems are prioritized to minimize reliance on energy-consuming methods. Natural daylighting systems, ground source heating and cooling, and circadian-based lighting design all help to improve the interior atmosphere. It is also important to note the human aspect of sustainable design. The proposal of any building element should not only satisfy environmental performance applications, it should promote a physically and mentally healthy working environment for all of the building's occupants. Overhauls to the 1021 building were reviewed by a well-accredited professional in order to evaluate their adherence to the WELL standard, which combines effective design and construction processes with health research. This method ensures that every design decision not only creates a healthy building, but healthy occupants as well. In keeping with human-centered design, this project seeks to uphold Virginia Tech's motto, Ut Prosum, or that I may serve. The incorporation of flexible event venues like an art gallery and an assembly space ensure that the 1021 building can serve its student body and the Alexandria community at large.
By renovating 1021, we are extending the life cycle of the building by capturing the embodied carbon. Trade-offs were made in upfront energy while installing a geothermal heat pump system in order to have lower operational energy use. The existing brick facade is wrapped in a soy-based rigid foam insulation, allowing us to increase the thermal insulation of the wall assembly and update the exterior cladding. This strategy gave us the opportunity to reduce end-of-life carbon by limiting demolition of the old building, as well as reducing upfront carbon by utilizing existing walls rather than resorting to new construction. Compared to a scenario where the existing building was demolished and required ground-up construction, keeping parts of the existing building lowered the embodied carbon benchmark from 834 kilograms of CO2 energy per meter squared to 220 kilograms of CO2 energy per meter squared. The form of the new addition allows for optimal daylighting for both buildings on campus, as well as retaining as much usable outdoor space as possible, including an upper and lower courtyard. Visual connections are created between the interior of the building and these green spaces through foldable Passive House certified nanowalls and triple glazed windows and doors. As you walk towards the entry of the building through the lower courtyard, you are greeted by the view of the makerspace above the entry, as well as being able to look out of the makerspace and see the green space below. Daylighting strategies echo the vernacular form of a shutter. The southern shading allows for the control of light and heat that is let into the building, while allowing visual connections between the auditorium space and the street. The east and west shading devices imply the shape of a shutter, as well as blocking the harshest light from entering through the windows. The vertical circulation areas are surrounded by 2 layers of polycarbonate and insulated with aerogel to allow light into the stairwell during the day and creating a lantern effect that illuminates the courtyards at night. We decided to retain the existing building envelope and add insulation to the outside to increase the R value of the walls. The materials used on the exterior include brick and bamboo panels, which are mimetic of the historic materials of the surrounding neighborhood. The brick is recycled and thus does not have a high carbon footprint as new materials do. The bamboo is made of laminated bamboo that does not use formaldehyde in its lamination process. These materials create the skin of the building, with brick as the overall material to retain its presence in the context of the neighborhood, and bamboo to highlight the new interventions such as shading devices and additions.
The design of the envelope was based on creating minimal waste from the existing building. Most of the exterior envelope is layered over the existing skin. The walls implement a double insulation technique in which we add a soy-based spray foam in the cavity of the existing metal stud wall and lay rigid rock wool insulation over the exterior. All of this is covered in a rain screen system with consideration for moisture trapping and mold and mildew growth through appropriate placings of flashings around the openings and seals around the entire envelope. The thermal properties of our proposed wall were then studied through Woofy 2D, and the efficiency of the added insulation is shown. The roof is covered with many layers of the same rock wool comfort board to achieve an R value from 62 to 76 from the new to the remodeled construction respectively. These 2 choices for insulation also offer significant reduction in off-gassing, improving indoor air quality. For the new addition's exterior walls, 6 inches of structural insulated panels latch to the CLT slabs to create continuous thermal protection, and soy spray foam stud walls once again help to increase the overall R value to 38. And as for the foundation needed a new addition, we considered using pressure-treated wood foundation, recognizing that the cement used in concrete foundation is one of the main contributors to the embodied carbon footprint of buildings. For our windows, we use the therm analysis to visualize the heat transfer of the existing and the new construction. The existing building's double pane windows are replaced with triple pane argon-filled windows with thermally broken frames to mitigate heat transfer through the envelope and taking on a U value of 0.14. The south-facing curtain wall will have a solar heat gain coefficient of 0.24, and all the windows will have a low E coating on the second surface from the exterior to reduce solar heat gain. Our aim was to decouple HVAC loads and have 2 different systems to monitor them to improve thermal comfort of the occupant. The hydronic radiant flow system handles the sensible loads, and the ERV system takes care of the latent loads of the building. The hydronic radiant flow system, in addition to being energy efficient, also brings about uniform heating and cooling of spaces, unlike the forced air system. This system is powered by a water-to-water geothermal heat pump situated in the basement, and by doing this, we are restricting the use of refrigerant to the basement. The geothermal heat pump makes use of the constant ground temperature to heat or cool the liquid that passes through the floors. The ERV system is designed to bring in adequate outdoor air into the building as per ASHRAE 62.1 standard. The system also transfers energy from the return air to the fresh air, thereby controlling the temperature and humidity levels. We have divided each floor into 3 thermal zones based on the volume and occupants. This will allow us to accordingly change the temperature based on the number of people using the space, thereby saving energy. An electric demand water heater is used to supply hot water to the bathrooms and the kitchen, which are centrally placed near the core of the building to reduce the amount of piping needed to transfer water. These pipes are made of high-density polyethylene to prevent leaks and maintain maximum durability. Fixtures have compatible flow rates below 1.5 gallons per minute to reduce water consumption. Energy performance was refined iteratively with Revit modeling and Insight energy analysis, the latter being a tool that leverages Energy Plus in its calculations. Our EUI targets to achieve a net zero energy were adopted from ASHRAE's Advanced Energy Design Guide for small to medium office buildings. Shifting the initial target source EUI of 75 to 68.5 and establishing a target site EUI of 21. Then achieving the source and site EUIs of 65.3 and 20.6 respectively. Our total solar energy generation amounts to an EUI of 27 kBtus per square foot, making this a net positive building. After improving the passive design, we moved on to adopt more energy efficient appliances and lighting fixtures and implement sensors for occupancy control, simulating notable reductions in the overall cooling loads. LED lights and occupancy sensors have been added to lower the lighting power density. As the students come in to work at any point of the day, this 24/7 occupied building requires occupancy sensors and time clocks to minimize energy use. In the larger, primarily day-lit spaces, photoresistors measure lighting levels and dim the fixtures as needed while providing a sufficient amount of illuminance for occupants. Sensors will also monitor rooms for movement to communicate with the smart power strips and sockets to shut off power when not in use. Desktop computers, monitors, printers, plotters, and scanners with power management modes shall be phased in, while staff and students themselves are encouraged not to leave device chargers on or other trickle drawers plugged in outside of use. Solar shingles, solar shades, and roof PV panels all contribute to generating energy for our building on 1021 Prince Street. By using as much as the building's roof area for PVs as we could and incorporating PVs on the sun-facing side of the southern facade's shades, this building alone is able to capture over 183,000 kilowatt hours annually. Savings to the electricity bill will accumulate to over $400,000 during the lifetime of these panels alone. Regarding the existing roof of our neighbor, the 1001, their solar shingles annually produce 75,000 kilowatt hours. Any excess generated is stored in saltwater batteries in the basement and fed back to the grid.
The more accessible and inviting entrance into the courtyard provides pleasant gathering areas for students and visitors alike. The connection to nature through water features and greenery provides a calming environment, and terraced landings increase connection to the street and the 1001 building. Seating, trees, and foliage activate the courtyard and create enjoyable views from within the building. The refreshment bar in the lobby features sliding glass windows that open into the courtyard, establishing an interior and exterior connection. As the building expands east, a rooftop courtyard is added above the parking entrance. This secluded courtyard improves the occupant experience by providing several amenities: a harvestable produce garden, a shaded work area, and flexible seating to accommodate gatherings of all sizes. This courtyard also provides a visual connection to nature for the north end of both buildings without obstructing any natural daylight. Finally, on the eastern side of the site, the former parking lot is repurposed as a looping driveway, facilitating ride-sharing and package delivery. There is also ample space provided for food vendors, with a small gathering area where students can grab lunch or wait for a ride.
As you enter the building through the courtyard, you are welcomed into the open and flexible gallery space. Locating the gallery as a lobby to 1021 enables an adaptable entry experience that achieves multiple qualities. First, you can showcase student work for visitors. Second, it inspires students with their colleagues' work. Third, it can morph into event spaces like a cocktail party with a refreshment bar tucked by a window. And lastly, it acts as a circulation and mingling space prior to proceeding past the pivoting panels into the assembly space. The pivoting tackable fabric wrapped panels create more gallery surface, support acoustic quality, and establish a transition threshold into the assembly. The assembly space itself is a vast tiered seating arrangement with multiple levels and stair depths to enable various types of seating and meeting. Looking out upon Prince Street, the assembly space in many ways also acts as a performance itself to those passing by along the street. A custom acoustic ceiling feature above frames the assembly space and orients seating viewers towards the open stage below. Moving up to the second floor, coming out of the newly renovated existing glass stairwell that is washed in light overlooking Henry Street, you come upon a flexible makerspace. The space features standing high tables and various plotting and printing areas to support expanded needs of occupants to lay out their work. One of the key needs identified for the space through the occupant survey were identified as flexible and collaborative small meeting spaces, natural daylighting, connections to nature, and options for informal workspaces. That need drove the interior design strategy, particularly on floors 2 and 3. Here we have another stretch of the pivoting tackable acoustic panels that create a pit space for students to meet for critiques and studio reviews. Along the windows at the Juliet balconies, we offer informal living room style meeting spaces. The southern end of floor 2, we see a biophilic wood pattern surround framing a classroom. To the north, we have studio desk in an open work setting but softened and delineated through biophilic pattern screens, integrated planners, and again the biophilic surround pattern marking the transition to the hoteling offices along the north wall. Beyond, you see where the second floor opens onto the upper courtyard and the first a series of collaboration booths. Up on the third floor of the space, we exit the stairwell into the student lounge and coffee bar that features banquette seating that opens onto a balcony overlooking the courtyard. Past the coffee bar is a continuation of studio workspaces. Custom wood-trimmed ceiling cloud features in all the studio spaces act to soften the studio space acoustically and experientially from the exposed ceiling. On this floor, we see again the biophilic surround pattern separating the studio space, but this time for an open collaboration space with living room style seating, a series of group work booths. The booths meet the need for semi-open group collaboration space with custom acoustic panels and screens separating them. To the north is continued studio workspace separated by a bank of enclosed huddle rooms for 2 to 3 people. This is also where we feature an enclosed quiet room with wall-mounted nooks as an intended place of refuge.
As we look towards a future, one free of this current global pandemic, we are all faced with this question. Do we seek to return back to normal? Or do we rewrite the playbook on what is normal? 1021 Prince Street renovation rewrites the playbook on a zero-energy building. It's a show-stopping embodiment of the future of architecture, one that recognizes the performance of the building is inextricably linked with the performance of human health.